Alright, so welcome back again to this video lecture in ENSC 106. And supposedly we are going to do indeterminate problems for members in torsion. However, I think that we also need to have problems on composite sections, right? So, for example, this problem has a varying diameters at some length intervals, and we have multiple points loading. Okay, so in that way, we can have an example for the force and deformation relationships. That's going to be summation. Okay, so this problem is taken from the textbook by Philpott, and this is example 6.4. The problem says a solid steel with a modulus of rigidity of 80 gigapascals, a solid steel shaft of variable diameter. Although it says variable diameter, this is actually not the. I mean, we don't need the integration method right here. We just need the summation methods for force and deformation relationship. Okay, so shaft variable diameter is subjected to the torques as shown. So we have torques right here. So multiple loadings, I mean torques at multiple points. And it says here at segment number 1 of the shaft, it has a 36 mm diameter, right? And segment number 2 has a 30 mm diameter, and segment number 3 has a 25 mm diameter. So right here, if this is our point A, point B, point C, and point D, so here's our segment number 1, and here's our segment number 2, and here's our segment number 3. So right here, I have included the diameter, it says here 36 mm, and I think I have to write this clearly. So we have 36 mm diameter and a length of 0.85 meters. Okay, so that's given, and for the segment number 2, we have 30 mm and a length of 1 meter. And for segment number 3, we have a diameter of 25 mm and a length of 0.7 meters. So right here we can see that there's actually a difference in diameter and difference in the length as well. Now for the torques, we have 900 Newton meter right here, and this is positive, right? Because we are following the right hand rule, and this one is negative, and this is 600 Newton meter. And right here, this is, I think this is 250 Newton meter. And we are asked to determine the internal torque. Actually, that's going to be the internal torque diagrams. Right, so what's going to be the torque in this segment? What's going to be the torque in this segment number 2? And what's going to be the torque in segment number 3? Okay, so we are going to compute for the internal torques and represent that in terms of a diagram. And for letter B, we are going to compute the maximum shear stress in each segment. So in this segment, let's say segment number 1, what's going to be the maximum shear? For segment number 2, what's going to be the maximum shear? And for segment number 3, we need to determine the maximum shear. And after that, we are asked to find the rotation angles. So this is basically an angle of twist, but in terms of a diagram. Okay, so by the way, this problem is the original figure for this problem is this one. So you would notice that I have drawn this differently because I've drawn this with a changing diameter and also the length. But the situation is that right here at point A, it's connected to an electric motor, right? And right here there's a bearing, and there are also a couple of bearings right here. That's because it says here The bearing shown allows the shaft to turn freely. Additional bearings have been omitted. Right, so meaning this is the input point. So that's gonna be in terms of the angle of twist. That's gonna be the something like the zero or the reference point, right? So if it twists right here, then it's not actually gonna be the same because there's gonna be deformation, right? So there's gonna be changes in the deformations along the length. I mean in terms of the rotation angles. Okay. Anyway, let's now solve this problem. Okay. So for the first step, we are going to um, draw the free body diagram for each segment. Right? So, for example, if I'm going to redraw this, so it's like something like this. And if this is my loadings, or I have to draw the labels first. This is B, C, and this is letter D. So I have to draw the loadings. It says here we have a 900 Newton meter, and right here we have a 600 Newton meter, and right here we have a 250 Newton meter. Right. So the first thing that I'm going to do is to make a cut. So let's say this is segment number 1, right? So I'm going to cut a section right here, and I'm going to draw the remaining portion. Right. So at this section cut, then what's going to be the torque, right? So let me redraw first this one. This is 900 Newton meter, and this is 600 Newton meter, and this one is 250 Newton meter. Okay, so if we apply the equilibrium equations right here, right? So we have 900 because this is clockwise. I mean positive torque, 900 plus 250, right? The minus 600, then that's gonna be the value of the torque right here. Okay, so let me draw first the torque, the internal torque, and let's write this is T sub 1. Okay, another one is I'm going to make a section cut right here. So this is segment number 2, and let me redraw again here. Okay, and finally I have to make a section cut right here. Okay, so let me redraw again. This is 600 Newton meters. So in this section we don't need to, I mean we don't need this value because we are only referring to this loadings or the portion of the shaft right here. right? And this one is 250, and right here this is 250. Okay, so what's gonna be the value of the torque? So let's just write this is let's just assume that this is the direction, and right here let's also assume that this is the direction, t sub 3, right? And let's label that this is, let's say, this is segment number 1, and this one is segment number 2, and this one is segment number 3. All right, so now we have this free body diagrams, then we can now apply the equilibrium equation to solve for the internal torques. Right, so let's start with this segment number 1. So T1, if we apply this, T1 is equal to, okay, so this is in the left hand side, so um, all the clockwise, all this rotation, clockwise rotation, that's, let's say, that's positive. Right, so T1 and minus 900 Newton meter, right, because this is opposite direction, and plus 600 Newton meter, and this one is minus 250 Newton meter is equal to 0. So if we transpose this to the right hand side, what we get is T1 is equal to 550 Newton meter. Okay, so the next is, let's solve for T sub 2. Right, so for T sub 2, this is T sub 2 plus 600, right, minus 250 is equal to 0. So if we transpose this, what we get is T sub 2 is equal to negative 350, right? So that means that the direction, this direction is not clockwise, but rather counterclockwise. All right, so that's going to be our direction. And for T sub 3, right, for T sub 3 is just simply equal to 250. Okay, so in terms of torque diagrams, so let's write here, drawing now the torque diagrams. Okay, so this is going to be our torque line. If this is our torque line, and let's say this is A, for example, this is A, and let's say this is B, and this is C, and right here is D. Okay, so you would notice that from this point A to point B, we have a constant torque, right? Because it's just loaded at, I mean, we only have this concentrated torques right here. So that's, I mean, that means that anywhere you cut the section in this segment 1, the value of the torque right there in this segment 1 is just simply equal to T sub 1. And this is positive. Why? Because of the right hand rule, right? So recall the right hand rule, it's like this. So if this is the, I mean, the thumb is the direction of the longitudinal axis, or the axis of rotation, and we are cutting in this side, so that's gonna be positive, right? So let's write it here. This is positive, so that's gonna be the value of T sub 1 is 550. So 550, and for T sub 2, just to the right of B, the value of T sub 2 is, it says here, negative 350. So that's gonna be right here. So negative 350. And for T sub 1, it says 250. So it's positive 250. Right? So this is gonna be our torque diagram. So from segment 1, I mean from point A to point B, that's just 550. And right here, from B to C, that's negative 350. And for D, C to D, that is 250. Let's write the unit. This is Newton meter. Okay, so now since we have this internal torques, then we can solving now for the maximum shear stress. Right, so what's going to be the shear stress in this portion, and then what's going to be the shear stress in this portion, and then later finally this portion right here, using the values given, the diameter, or in terms of radius, and the length, and also the shear. I think it's just one material, so we just have to use um, let's just write this equation. Right, so our working equation is just simply T R all over J, right? And the value of J, uh, the value of J actually changes because we have a different diameters in segment 1, and segment 2, and segment 3. Right, so let's just write this equation. So for shear sub 1, that means that the maximum shear at segment 1 is just equal to the torque, and the torque is 550. So this is 550 Newton meter times the radius. Now what's the radius? Um, by the way, if we'll use, I think we'll use millimeter. So 550 times 10 to the 3 Newton millimeter times the radius of 36 divided by 2, that's 18. And for the J, actually this J is, since this is just a solid shaft, this is pi over 32 times d to the fourth, right? So that's our equation for the polar moment of inertia. Right, so this is pi over 32. Then what's the diameter? See, that's 36. So 36 to the 36 mm to the fourth, right? And what we get here is 60 megapascals. And for the shear stress at segment number 2, this is 350, right? So this is 350 times 10 to the 3, and we have the same units, times the value of radius, so 30 divided by 2, this is 15, divided by pi over 32 times the diameter, 30 raised to 4, and what we get here is 66 megapascals. And finally, for segment number 3, the maximum shear stress is, this is 250 times 10 to the 3 times the, what is this, the radius. So the radius is 25 divided by 2, so this is 12.5 divided by pi over 32 times 25 raised to 4, and what we get here is 81.5 megapascals. Okay, so we have now solved for the maximum shear stress, and finally we are asked to find the rotation angles. Okay, so for the rotation angles, solve first for the angle of twist. Right, so for the angle of twist, our working equation is just simply TL all over JG, and this And the same as what we did in the stress, then we solve for the angle of twist from point A to B. And this is T sub 1. Our torque is, now let's write it here. Let's just write a value. So this is 550 Newton meter, and just have to raise this, multiply times 10 to the 3, because what we need is a millimeter. So T, that's our T, and our L is, this is 0.85, right? This is 0.85, so it's not that clear. 0.85 meters. So if we translate that to millimeters, that's just 850 millimeters. And for our J, so our J is pi over 32 times the diameter of 36 mm to the fourth, right? DL all over JG, right? So our G is, that's given, this is 80 gigapascals, but I have to be consistent with my units, so this is 80,000 megapascals, because megapascals is Newton per mm squared, right? So if we do the calculations right here, what we get is a value 0.35439. This is in radians, right? So that's the value of the angle of twist in this segment. Now for segment number 2, we just substitute all the values. Negative 350 times 10 to the 3, and for the length we have a 1000 millimeter. So this is 1000 millimeter divided by pi over 32, and the diameter is 30. It's 30 to the fourth. What else? Times the 80,000, right? Megapascals. So this one, what we get is negative 0.055017 radians. And finally, for the angle of twist for segment number 3, this is 250 times 10 to the 3 times the length. So the length right here, this is 700 millimeter, so 700 mm, right? So we don't need to write the units. Divided by pi over 32 times the diameter of 25. Sorry, this is 25 mm. So 25 times 10 to the 4, and the modulus of rigidity is 80,000. Right, so this one is 0.057741 radians. Right, so here's our value for the angle of twist. And in terms of rotation angles, let's write here, in terms of rotation angles, then the I think this should be, if this is our reference, so the angle of twist must be at this point B, right? So if you recall in our figure, original figure from the book, since this is the electric motor, then that's gonna be the starting point. So the twist, I think this twist right here, must be the twist at point B, right? Because if you recall, if it's something like this, so if this is our main point, and if this is fixed somehow, so there's gonna be changes, right? So this one, let me draw it. a little bit bigger, right? So it's something like this. So this is point A, and this is point B, and if this is our reference point, then the angle of twist is right here, right? So that's gonna be the value. This value is this one. So this will be B, and this will be C, and this will be point D. So therefore, for the angle of twist for the segment number 1, this is just simply the angle of twist at point B minus the angle of twist at point A. Right, so let's just write here point B minus point A. Our point A is just 0 because that's something like the reference or the starting point. And for segment number 2, this is just simply the angle of twist at C minus the angle of twist at B. And for segment number 3, this is D minus C. So in terms of, so let's write it here. Right, so segment number 1, this is or I guess we should rather I think we should rather I think I was confused with this. I think there should be, if we are going to use these equations, then this must be the angle of twist at segment number 1, this is segment number 2, and this is segment number 3. Right, so sorry for that. This must be segment number 1, segment number 2, and segment number 3. And this one, this refers to the angle of twist at point B. Right, so if we substitute, if this is our reference point, right, this is our reference point, that's A, so this will be actually 0. So what we need to find is actually this what we need to find is this angle of twist at B, at C, and at D, because we are going to plot that in a diagram, something like this. Okay, so from this equation, the angle of twist at B is just simply this, right, let's just use the theta right here. So this is theta 1. Okay, so if we transpose this, actually this is just 0, so theta base is just equal to theta 1, which is just equal to 0.035439, 0.035439 regions. And for to find C, this is equal to the angle of twist as segment number 2 minus actually not minus, because you are going to transpose that to the other side. That's going to be plus plus this one, which is this value, right? So the angle of twist at segment number 2, this is negative 0.055017. This is the value. Okay, plus this one, so 0.035439 radians. Then if we compute this, what we get is, so let me compute this, 0.035439 minus 0.055017. So we have negative 0.019578, right? So sometimes this is I don't know why we need to write this decimal numbers. I mean, this long, right? Probably we can do like 4 decimal numbers or 3 decimal numbers. Right, so that's the value at C. And now for letter D, that's just the angle of twist at segment number 3, okay, plus C. Right, and this value is this one, 0.05, right, 0.057041, right, plus, actually that's minus, and this is minus 0.019578, and this one would be 0.037, something like 0.375. Okay, so in terms of diagram, it's like this. So if this is our rotation angle, and let's say this is our, sorry, this is our point A, and this is our point B, and right here point C, and here is point D. So our rotation angle is from point A, this is 0, right? So we have a 0 value, and at point B, this we get a positive value of 0.03. So let's say this is it. So this is 0.0354. Let's write this in radians. And at point C, it goes to negative 0.019. So let's say it's something here, so somewhere right here, negative 0.0196, for example. And for point D, this is positive 0.0375. So 0.0375. Let's write 0.0375 radians. Right, so this is gonna be our rotation angles in terms of diagrams. Okay, so I guess that's a lengthy discussions regarding the sample problem. But anyway, it's another type of sample problem, because here we have a varying cross sections and different lengths and multiple loadings, right? So I think that's all, and in the next video we'll do an indeterminate problem.